Another place we can look for clues about the formation of a solar system is to look at planets orbiting other stars. And that is what an exoplanet is. That is a planet orbiting another star. And when we look for exoplanets, one of the first places we can look is where stars are forming. And when you look in a star formation region, in this case we're looking at the Orion Nebula, we can see forming stars. Each one of these little balls in this picture is a forming star. And roughly half of the forming stars that we can see are surrounded by a disk of material, and we call that a circumstellar disk. And the thought is that that disk of material will ultimately form into planets orbiting that star. And of course, one of the clues with our own solar system is that all the planets are in the same plane. Well, a disk will force them into the same plane, and all the motions are in the same direction. And the rotation of this disk would then get transferred into the motion of those planets. Once you actually have a star with a planet orbiting around it, we have a very hard time actually seeing the planets. There are a small number of actual photographs of planets next to stars because the planets are so small and so faint, whereas the starlight just completely washes out anything around it. So one of the ways that we can look for a planet is by its effect on the star. And so what we're going to look for is called StellarWobble. In this picture, we've got a star, and we've got the planet orbiting around it. And this is highly exaggerated, but if you picture that star and that planet, ignore that second star, then we can picture them as being, for example, on a teeter-totter. And so, the star is bigger, the planet is smaller, so it's just like a big kid and a little kid. Your balance point is going to be closer to that big kid. And so as a planet orbits around the star, it's actually orbiting around that balance point. And if the planet is big enough, that star is also going to orbit around that balance point. And so the star is in motion. We can measure that motion. We can use the Doppler shift to measure it. We can get a blue shift as the star comes towards us and a red shift as the star moves away from us. And that's what the wobble is that we're going to measure. This particular technique is kind of biased as far as what kind of planets it most easily finds. It's going to find planets that make the star move the most. And the ones that are going to make the star move the most are going to be close to the star, and they're going to be quite large. The ones that are close to the star have the advantage of time, because when we're measuring that wobble, we want to see that star going back and forth a couple times to confirm that it actually is moving. So that means we need to watch it for 2 or more orbits. Well, in the case of the Earth, of course, it takes us 1 year to orbit around the Sun. So to observe us, it would take 2 or more years to confirm a planet. You get out to something like Jupiter, it's close to 10 years to orbit around the Sun. So 2 or more orbits, you'd need to be watching it for close to 20 years. So just the bias of time is going to lead us to find planets close to the star. The other bias is that we need to actually be able to measure that motion. We're measuring Doppler shift. And recall the way we measure Doppler shift, we're looking at spectral lines. And so if that star is moving a lot, well, those lines are going to shift a lot, not as much as I'm drawing it, but to emphasize the point, you're going to get a large shift if the star is moving a lot. If that star isn't moving a lot, then it's going to be very hard to tell if there's a shift or not. So we need a big wobble to actually be sure that we're measuring a Doppler shift. Well, the kind of planet that is going to cause a big wobble is a big planet. So this technique is very biased towards finding big planets. So if you have a large planet close to the star, that means you've got something comparable in size to Jupiter, but orbiting at distances similar to Mercury. So these have been dubbed hot Jupiters. And there's a problem with that. When we talked about our solar system, how the temperature of the sun dictates composition. Well, at these kinds of distances, you should not get a big gassy planet. Those need to form in cold locations. So one hypothesis is that here's our star, and here's the disk of material that the planets are forming out of. That these planets formed, but they didn't use all the material in that disk. So, as they're traveling around, that disk is causing drag, and it's actually slowing the planet down and causing it to spiral inward. Once the disk is clear, then the planet's going to settle into a stable orbit. But as long as the disk is dusty, it will continue to get pulled into the star. So there's a possibility that these planets actually formed much farther from the star, but have worked their way in closer to it. The heat of that star should make all of this atmosphere evaporate over time. So this planet would not be stable at these close distances. The StellarWobble technique we've been using since the 90s, but in the more recent years, we have put a telescope in space to try to find planets, and that's the Kepler telescope. And instead of looking for Wobble, Kepler is designed to look at the light from the star. And if we're looking at that star, and we happen to be lined up just right, that the planet comes between us and the star, then that planet's going to block some of the light. And if we measure the light of the star while the planet is in front of the starlight is going to dip a little bit. It's going to look fainter. And then once the planet has stopped being in front of the star, the light from the star will go back up to being a little bit brighter. So Kepler has been looking for these dips in light. Once Kepler has a good candidate, we go back to the StellarWobble technique to confirm it. Well, at the time that I made this program, which is summer of 2014, close to 1,800 planets around other stars have been confirmed. And this graph is showing the size of the planets and the mass of the planets, and it's done relative to Jupiter. So this is showing radius compared to the size of Jupiter, mass compared to the mass of Jupiter. So on this scale, 1 and 1, roughly in there, that would be the size of Jupiter. So everything above this line is heavier than Jupiter, and everything past that line is larger than Jupiter. So we're still biased towards finding big planets because big planets are going to block more light. But what's exciting is the stuff down in here, because that is getting into planets closer to the size of Earth, and those are the ones that, of course, make us very excited. Now that last graph was what's been confirmed. Remaining to be confirmed are about 2,000 candidates. And this graph is showing orbital period versus the size of the Earth. So this line right here is the size of the Earth. So we have candidates smaller than Earth, though certainly still a lot more that are bigger than Earth. But we're still looking at pretty short orbital periods, 100 days. It takes us 365 days to go around the sun. So we're still seeing things that are relatively close to the star, but we are also starting to find quite a few objects that are closer in size to Earth than we've ever found before. So it's all going to be very exciting to see what all we can find out there.